Well, hello once again, AP students. So today we're looking at a topic that should be somewhat familiar to you. This transcends actually a couple different topics in the AP curriculum, the AP calculus curriculum. But anyway, vertical and horizontal asymptotes. And these are both situations where the function is either going off to infinity or as x is going off to infinity, positive or negative, that we're looking at the end behavior model of what's going on with a function. So first of all, the idea of a definition of a vertical asymptote. So if either the function is going off to infinity or negative infinity from either the left-hand side or the right-hand side as x approaches some specified value, then that specified value, x equals c, is going to be a vertical asymptote. So again, the function is going off, but in particular, as x is going to a specific value, not necessarily infinity or negative infinity, like a parabola might be. There, the function is going off to infinity, but of course, those are not vertical asymptotes. So again, the function's undefined there typically at x equals c. And if you remember from your pre-calculus days, if you simplify your expression, it's typically a rational expression where this occurs, a polynomial over a polynomial. And in that scenario, then if you simplify that expression, looking at taking your removable discontinuities out, simplifying the expression as much as you can, the zeros that remain of the denominator then would be your vertical asymptotes. So again, that might look something, excuse me, I'm not sure why that went that way, but let's see if I can't get back. I'll just make a simple one here. If you had x to the x squared minus 4 over x minus 2, and the limit as x goes to 2, by direct substitution, of course, the numerator go off to 0 and the denominator go off to 0. That's again called an indeterminate, and you can't determine the value, what's going on there. But you recognize that if you simplify those expressions, do a little factoring in that numerator, and that when x equals 2, that is actually a removable discontinuity. Those factors would simplify to 1, and now that limit would be 4. And so the situation there, the limit would be 4. I don't have a removable discontinuity, excuse me, I didn't have a remaining denominator. I should have turned those up the other way around, x squared minus 4 in the denominator. But anyway, the idea is simplify the expression as much as you can. The zeros of the denominator, of course, end up being the vertical asymptotes, x equals those values. And the zeros of the numerator end up being the x-intercepts. So this was actually giving me the x-intercept was going to be at -2 of this function. But the limit would be approaching 4 as x gets to 2. All right, so then we look at also the definition of a horizontal asymptote. The scenario here now is the function itself is going off towards infinity or negative infinity. And if that's approaches a value, either from above or below, or even crosses it, that then would be the horizontal asymptote would be the line y equals L. And so this is a little couple acronyms here to help you remember what's going on. The 3 calculus clowns. This is based upon the degree of the numerator and the degree of the denominator. So if it's the degree of the denominator is bigger than the degree of the numerator, bigger on the bottom, then your horizontal asymptote is y equals 0. And if the degree of the numerator and the degree of the denominator are the same, both the same, then it's just the ratio of the lead coefficients. So if you had y equals ax to the m, where that's the lead term, and bx to the m, the degrees being the same, both m and the degree in numerator and denominator, then the horizontal asymptote in this case would be y equals the ratio of those lead coefficients a to b. And then if the degree of the numerator is larger than the degree of the denominator, bigger on the top, no, there's not a horizontal asymptote. And if they differ just by one, it's an oblique asymptote. And so that would be a slanted line. And again, as x goes to infinity, or as x goes to negative infinity, then the function would be approaching that line y equals mx plus b. That again only occurs when the difference between the numerator is one larger than the degree of the denominator. And otherwise, you have some other type of end behavior model, possibly a quadratic, cubic, whatever the case might be. But in those situations, you do not necessarily have horizontal asymptote, but possibly oblique asymptote. So you'll be responsible for knowing that idea of oblique asymptotes, again, only happening. But there's a pretty good way, hopefully, to remember then the three calculus clowns, Bobo, Bosco, and Botno. Those of you who had me before have heard me say these to you in pre-calculus, but those actually came from some calculus notes a couple years back. So anyway, horizontal vertical asymptotes, probably not a difficult topic for you, but again, one to review with you as again affect limits and what's happening to the function or happening to the end behavior models. Let me just make one more side note here on those vertical asymptotes. There is a little bit of, it seems like some contradictory material here that when we get to unit 3, we're just going to say that those limits are infinite, as saying those limits are equals infinity. Of course, infinity is not a number, and by the definition of limit, it has to go to a particular number. So this is splitting hairs just a bit, but anyway, recognize we read those as the limits are infinite as compared to going to infinity, or are infinity or equal to infinity. All right, so we only have one more video here for unit 1 that we're going to take a look at, and then we'll wrap these things up that first week of school when we come back and have a chance to look at unit 1 altogether. Thanks so much. We'll see you next time. Bye now.